Okay, hi everybody. So just to remind you where we were from last lesson, we were looking at defining the derivative as the gradient function, that if we had a function f of x, we could work out the gradient function by considering what the tangent to the graph would be like if we move 2 points really, really close to each other. So I finished off with 3 problems that you had to choose one and do. So one was to show that, I'll just change colors there. One was to show that if f of x is equal to 3x, then f dash of x is equal to 3. The second one was f of x equals x plus 1 all squared, then f dash of x equals 2 outside of x plus 1. And the third one, which is the hard one, was it looks deceptively simple, but to show that if f of x equals 1 on x, then we have f dash of x is equal to negative 1 on x squared, isn't it? That's what I asked you to do. So it's that third one which was quite tricky, I think. Who had a crack at I don't care if you didn't get there, but who had a crack at the third one? Yeah? A couple of you? Did you get there? You got there, Sam? Good on you. Well done. At the risk of boring Sam, I might just go through it just as an example again, just to start the lesson off with the limit theory. While you're waiting, do the other two for us, Sam. See, the reward for good work done is more work. That's the reward. So try and do the other two. So just again, nomenclature, language warning. F dash of x is the gradient function that is derived from the original function. Okay, so we call it the derivative. Okay, so f dash of x is the derivative, is derived from the function f, and what it gives us, remember, is the gradient function. Okay, it's a rule that we can use to work out the gradient at any point of the function f. That's why we're doing it. Question on that? Okay, so we have f of x, f of x is equal to 1 on x. F dash of x, we know, is worked out by considering the limit as h approaches 0 of the change in y over the change in x. And we know that when we go x plus h minus x, we're just left with h. So we always start, when we're doing this, we always start with that particular statement. Now, what I got the strong feeling from last time is that people were really confused about what to do with f of x plus h. So I'm going to just spell that out. Even though this is the most complicated problem, the process works for every single function that we can think of. So I just want to spell that out a little bit. So the next line, because I haven't taken h to 0 yet, I do need to include this. People are going to get really annoyed about having to write limit h approaches 0 every single line, but you have to. Limit as h approaches 0. Now, f of x plus h. So if I look at the original function here, f of x equals 1 on x, what I'm saying is, if I sort of unpacked it, I'd be saying I have a rule. And my rule is, for whatever number I'm given, or the input number, I have to go 1 over that input. Okay? So we call the rule the workings of the function. We call this the output of the function, or the y value, and we call this the input of the function, or the x value. So remember Dix-Roy, domain, input, x value, Roy, range, output y value. So there's the input, there's the output. If I go f of 1, we know that means 1 on 1, right? If I go f of 3, we know that's 1 on 3. Yeah? Input is 3, output is 1 on 3. Input is 17, output is 1 on 17. Input is 0.1, output is 1 on 0.1, which we can then simplify. Okay, so here, I know it looks tricky, right? But at the end of the day, all this says is that the input is not just simply x, but x plus h. So the input is x plus h, the output is 1 on x plus h. You follow the rule, okay, that you're given. So I have here, it's horrible, it's fractions on fractions, but you know what? We'll deal with it. 1 on x plus h, f of x, the input is x, the output is 1 on x. So it's 1 on x plus h over 1 on x, and the whole thing is over h. Now, just a reminder that the name of the game with these limit theory things is to remove the impossible. At the moment, if I slid the value of h to 0, then I would have a fraction over 0, which is impossible. So we need to manipulate it until the impossible is gone. Sounds dumb, doesn't it? That's what you're doing. Okay, so I need to continue to manipulate my equations until I can do that. I'm not there yet, so I'm going to continue going. I see that I've got this. I might even zoom up so you can sort of see what's happening in grand scale here. I've got this really complicated looking expression here, so I'm going to try and simplify it. So I'm going to find a common denominator, and the easiest way of finding a common denominator is to multiply, each fraction by the opposite denominator. So I end up with x on x times x plus h minus x plus h on x times x plus h all over h. Is that okay? Let's simplify the top there. So f dash of x is equal to the limit as h approaches 0, so that we can see it all at once now. So I've got x minus x plus h. Now I'm just going to take this slowly because I don't want there to be any confusion here. If I subtract those numerators, it looks like this: x minus x plus h all over x times x plus h all over h. It's a fraction over a number. It's all good for the time being. Now, whenever I'm subtracting something which is compound like x plus h, I always take an extra step and put brackets around it so I don't stuff up my negatives. Because I hope you can see here now that top part of the fraction here is going to be x minus h all over x times x plus h, and the whole thing is over h. And now hopefully you can see that on the top here, x minus x is 0, so I'm just left with a negative h. So the limit as h approaches 0 of negative h over x times x plus h all over h. Nearly there. We've broken the back on this one, believe it or not. Now, the next thing depends upon your experience with fractions. When I have a fraction over a number like this, my instinct, and I'm going to spell it out, but I'll probably just do this in one action, really, if I was doing it just by myself. But my instinct is to take the bottom part of the fraction and turn it into a division. So it looks a little bit like this. So that's equal to the limit as h approaches 0 of negative h on x times x plus h divided by h. See what I've done there? I've just put the over h at the end there and turn it into a division by h. Yeah? I hope. Now, again, if your fraction knowledge is really weak, the next thing's going to look like mathemagic. But I hope you know that if I divide by a number, it's the same as multiplying by its reciprocal. I flip it. And if I've got a number by itself like h, then the reciprocal of h is 1 on h. Okay, so this will be slide 4 now. F dash of x, nice, f dash of x is equal to the limit as h approaches 0 of negative h on x times x plus h multiplied by 1 on h. And this is nice because I've got an h by itself here and an h by itself here. So I've eliminated the h and replaced them with a 1. And that gives me the limit as h approaches 0 of negative 1 over x times x plus h. Okay, I'm going to stop there for a moment, ask if there are any questions before I move on to the next step. You might be able to finish it yourself now, I don't know. Now, common complaint that's rarely voiced, but is often, I can often hear it echoing in their heads while they're thinking it, is I would have had no idea how to, that I would have had to have done that. I would have had no idea. Obviously, you can do it because you're a teacher, but how was I supposed to know to do that? And the answer is not, you don't really, but a good mathematician isn't someone who knows how to get from A to Z in the neatest path. A good mathematician is someone who says, what could I do next? And if you think about it, going from here, which is just, starting here is absolutely necessary because there's no other way of starting a limit theory problem. Replacing the functions with their expressions, there's no other thing to do. Going from here to here is like, how can I simplify it? How can I move forward? And that's where your mathematical thinking has to come in. Not like this will get me to the solution, but what could I possibly do? In this instance, it was, well, I could find a common denominator and try and see if I can simplify this fraction. That's the thinking you have to have. Not if I do this, it will get me the answer, but what could I possibly do? And be prepared for dead ends when you try to go down a pathway and it doesn't get you anywhere and you have to backtrace and try a different way of getting there. That's what makes a good mathematician, not someone who can say, I know the straightest path. It's often confused by teachers who always take the easiest path because they've prepared it beforehand and they know it already. But that's not in practice how it works. You take any pathway you can. Okay, I'll get off my soapbox. Here we go. We've now got it to this stage. I've got rid of that h all by itself. So again, keeping an eye on the prize, I want to make sure I've got something left when I slide h to 0. And now I can see that when h gets zeroed here, I'm not going to be left with an impossible expression. Okay, so now I'm ready. Before then, I wasn't, because that would be 0 there, for example, on that line. Or if I just slide over a bit, dividing by 0 here. Before then, I would have been dividing by 0. So it would have given me an impossible expression. Whereas now, it won't. So now I can slide to 0. So I get rid of my limit as h approaches 0 thing, and I'm left with negative 1 multiplied by x times x, which equals negative 1 on x squared. And because you've got a negative over a positive, just FYI, this would have been fine. Just leave it like that. But just to confirm that I can say that's negative 1 on x squared. 1 over x squared is a positive number, and then make the whole thing negative. It's the same thing. And that's what you had to prove. Yeah? Methodical, step-by-step processes. That's all you have to, well, it's as simple and as hard as that, right? I'm not trying to suggest that it's like really straightforward, but it's as simple and as hard as that. Does anyone have any questions before I move on to the next piece of work? Okay, so what we've just been doing for the last couple of lessons now is when we've been looking at limit theory, and in particular looking at the limit theory where we're finding the gradient function, is we're doing a process called finding the derivative by first principles. And when you see that phrase, and you will see it in the exam at the end of the year, and you will see it in tests, and you will see it in the assignment I'm about to hand out, when it says find the derivative by first principles, it simply means the very fundamental principle of the way derivatives work is difference in y over difference in x, and this is what this allows us to explore. Okay, so it is a required skill. It is a good, particularly those who are continuing on to 415 next year for the year 11s. It is useful to have that deep understanding of what's going on with derivatives. But here's the good news. It's not what you do in practice when you're trying to find the derivative, when you're trying to find the gradient function. In practice, there's a rule that you follow. And if you've done Maths Extended last year, and of course the X415 students would absolutely know this, the rule is quite simple. I'm going to apply, I'm now going to tell you what the rule is. I'm then going to get you to practice it a little bit, and then I'm going to link it to some other stuff that we need to do. Okay, so this is worth putting into us in your summary book. This is just going to be so cathartic to know that the rule is so straightforward, really. So given a function where you've got a multiplied by x to the power of n, and that's it. Now, I'll give you some examples so you can see it in practice. But that's basically it. So if you have a function, then all you do to work out the gradient function, sorry, a power function, I should say, then all you do to work out the gradient function or the derivative is to bring the power down here. So multiply an a and n, sorry, the cursor's in the way. Multiply a and n together, and then subtract 1 from the power. That works for every single kind of power function. And I want to unpack what a power function is in a second, but all polynomials are power functions, and there are a bunch of other ones as well, which we'll have a look at in a second. So I'm just going to put the simplest of examples here just to give color to it. E.g., f of x equals 3x squared. F of dash of x equals 3 times 2x to the power of 1, which equals 6x. Because anything raised to the power of 1 is just itself, right? Now, the good news is it works for any power of x. So let's put some examples here down so we can sort of get it. So note, it works for constant functions. F of x equals 3. Oops. F dash of x. Give you a second to think about it. F dash of x. If f of x equals 3, using the power rule, what does f dash of x equal? I'm going to ask for an answer, then I'm going to ask for an explanation, and then I'll briefly write that explanation down. Oscar, I'll pick on you. What's f dash of x?
0.
Yes. F dash of x is equal to 0. Any constant it's called differentiation, by the way, when differentiated, when you find the derivative of it, is just equal to 0. Leo, why? Lo, what power? There is no power there. Not quite. Not quite. You're right, it's got to do with the powers because it's the power rule for differentiation. You're right, it's got to do with the fact that it's 0, but there is no power there yet. Can anyone see a power of 0 in there somewhere? Okay, let's put it a different way. Declan, what's 10 to the power of 0? Eliza, what's 3 to the power of 0? Alice, what's 1.5 to the power of 0? Emily, what's negative 10 to the power of 0? Anything to the power of 0 is equal to 1. Okay, so hidden inside here, we have f of x equals 3x to the power of 0. It's just hidden, right? The power rule says the first thing I do is I bring down that power that I start with. And I subtract 1 from the power. This doesn't matter what it is, because when I multiply anything by 0, I get 0. So Leo, does that crystallize where that 0 is coming from? We are absolutely, legitimately putting in an x to the power of 0 there, and that's why all constants return to 0. Well, I should say it fits the power rule still.
How would you put that through the limit theory?
Really easily, to be honest. Don't write this down. I'm just going to answer Alex's question. It's actually really easy. F dash of x is equal to the limit as h approaches 0 of x plus h minus f of x all over h. Now the thing about this function says I don't care what the input is, the output is 3. I can put in any number here, I'll just output 3 every single time, which means f of x plus h is just 3, f of x is just 3, 3 minus 3 is 0, which is 0. Now if I set the limit h equal to 0, I'm still going to get 0. If that didn't make sense to you, it doesn't matter. No, I mean it. If you get it, you get it. If you don't worry about it. Important thing is you can use it the power rule at this stage. Second point. Look at the easy function that we did. Do I still have it on the board? I don't. I'm just going to zip back just for a second. That's a linear function, right? We can see that f dash of x is equal to 3. Okay? So just from our easy example there, if I have f of x equal to 3x, then f dash of x is equal to 3. Now, I'll spell this out because I'm probably taking too long for the theory. Because f of x is equal to 3x, and we don't normally write it, but it's 3x to the power of 1. So when I use the power rule, f dash of x is equal to 3 times 1 times x to the power of 1 minus 1, which is 0. X to the power of 0 means it disappears, because anything raised to the power of 0 is 1, and 3 times 1 is 3. So it works for linear functions as well. And I just wanted to point out, that's the gradient. And for a linear function, the gradient is m, like y equals mx plus c. So if you think about it, Again, don't write this bit in red down. We know that all linear functions can be written as y equals mx plus c. Have a look at this. If I find the derivative of this, the x disappears, leaving me with m here, and c is a constant number, and that bit we know from over here goes to 0. So we get m plus 0, which is m. So everything we've done up to now in terms of linear functions is confirmed by our gradient, our work with derivatives. It works for linear functions. And the last thing, I think I'll put it on the next slide. The last thing I wanted to say, I think, oh no, second last thing. It works for negative powers. Now, what is a negative power? So, hang on, I'll do it this way. If I look at f of x equals x to the power of negative 1, what's the effect of a negative number? What does it do to our, if I have 3 to the power of negative 2, can anyone remember what happens with a negative power? We did it in our indices last week, or the week before. Yeah, it's 1 over, right? So f of x equals x to the negative 1 is equal to 1, on x, okay? Now, using the power rule, that's equal to negative 1 times x to the power of negative 1 minus 1, which is equal to negative 1 times x to the negative 2, which is equal to negative 1 on x squared. Okay, how do I know that works? Well, I'll flick back to this screen in a second. Didn't we just spend the last 10 minutes or 15 minutes doing it here? We started off with f of x equals 1 on x, which is actually x to the power of negative 1. And we can see by using first principles, I get negative 1 on x squared. This is what we got from first principles. It is confirmed that the power rule would give us the same result because a fraction can be written as a negative power. Okay? And you can see that it will give me the same result. So that's cool. And one thing I'm not going to demonstrate, but I'm just going to do an example, is that it works for fractional powers. So if we have f of x equals the square root of x cubed, let's just say that's our function, it's still a power function. And the reason why is because f of x equals the square root of x cubed can be written as x to the power of 3 over 2. Okay? Because a to the power of a half is equal to the square root of a. So you've got to remember that relationship. That's why we reviewed our index laws before we started our calculus unit here. A to the power of a half is root a. So x cubed square rooted is x to the power of 3 on 2. Therefore, f dash of x equals 3 on 2x to the power of 3 on 2 minus 1. So 3 on 2 minus 1 is going to be a half. So we'd have 3 on 2, x to the power of a half, or 3 on 2 root x, or 3 root x on 2. All of those are legit answers there, or both of those last lines there are legit. That's about it for that. What do you reckon? So importantly, genuinely, we can see it links back to the first principle work we did originally. We can see that the power rule will work regardless of the sort of the format of the function there. There's a couple of other things I'm going to write that get you to write down into your summary books to make sure it's really explicit. And then I'm just going to get you to do a whole bunch of practice. So we're nearly at practice stage now. Now these notes will be available on Google Classroom a bit later, but I'm just going to switch over to the next one now, if that's okay. I'm just trying to think about how to write this concisely. So I hope this is okay. So this is still under the notes. So the rule works over addition and subtraction by applying it to each part. E.g., if I have a function, sorry, Alex, if I have a function that's made up of a whole bunch of powers, so 3x to the power of 7 plus 4x cubed minus 2x minus 100, then f dash of x is equal to 21x to the power of 6, that's that bit, plus 12x squared, that's that bit, minus 2, that's that bit, and then the minus 100 disappears because it's constant. So you apply the power rule to each part. So leave it out. Yep. Good question. Leave it out. Really critical, this next part. That's why I'm putting an underline, exclamation marks at the end to make it more exciting. It does not work over multiplication and division. It does not work. Okay? We've already seen this. I'll do an example here, but you can see that that if you look at that hard example that we did, I'm just going to flick over briefly. I will come back to this screen. If we look at this one here, if I said, oh, well, that's one part at the top and one part at the bottom, the derivative of 1 is 0 and the derivative of x is 1, I'd have 0 over 1, which is 0. That is not what the actual answer is, right? It's negative 1 over x squared. Okay? So that's just an easy one. I could choose a harder one, but the point is that I can't find the derivative of each part here. I have to find a different way of doing it. In 415, do you do the product rule and stuff like that? Yeah. So you can use it in this course if you want to. There's no harm in doing it, but you won't get problems that are hard enough to have to use it. Yeah. So a non-example, I suppose. So e.g., what do I have for an example here? Oh, I don't have one. Okay? I'm not even going to, it's so disgusting. I'm not even going to finish that problem because it's so entirely wrong. So if I've got two expressions multiplied together, which typically you get it all the time, a factorized expression, you can't factorize each part of the expression. You just can't do it. It does not equal, it's in red there as well, 2x times 5x to the power of 4. It just doesn't equal that. So a quick question before I get you stuck into doing some problems from the textbook. How would I mean, 415, shush. How would I solve that problem if I was given f of x equals x squared plus 3 times x to the power of 5 minus 2, and I was told find the derivative of that, find the gradient function? What would be, don't do it, but what would be my approach? Alice, what do you think? Perfect. Yep. So in almost every single instance, if you're not given a sum or difference of powers, you need to do something to get it into a sum of powers or differences, pluses or minuses, so that you can use the power rule. Next year, if you do 415, you'll learn special rules called the product rule and the quotient rule, which will allow you to directly do that. But the problems that we do this year, you don't need to worry about. It's just a matter of manipulation. So in subsequent lessons, what we'll be doing is we'll be saying, well, how do we tackle it if we do have, say, a fraction with a power on the bottom? How do I deal with that sort of thing? So we'll build our toolkit up so that we can solve a whole bunch of different problems in the same way. So what are you going to do now? For the rest of this lesson, so for the next 20 minutes or so, I want you to go to your textbook, and I want you to go to page 589, which looks a little bit like this. If I could have your patience just for another minute or two, then we'll be right to go, guys. I'm not going to say this. I'm not going to write this down. So if you don't hear my instructions and you do too much or too little, it's your problem. So you will see that questions 1 through to 4, you're asked to basically just apply the power rule. You do not need to use first principles for this. You're practicing the power rule. It's really straightforward to use, but practice will make you efficient at using it. So you'll probably, if you've never come across it before, you'll probably need to think about it and then write it down. But by the end of questions 1 through to 4, you should be right to do it. Just to show the difference between the ones here, you've got, it just says find the derivative of each of the following. That's pretty straightforward. It's just not, you're just not told f of x. The second one just introduces that f dash of x notation. So remember, f dash of x is the derivative. In question 3, it says find f dash of 1. So I don't want to belabor the point, but you know that means substitute 1 into the function. But don't forget f dash is its own function. It's the derivative from f, but it's its own function. It's a gradient function. So all it means is that step 1, find f dash of x, and then step 2, substitute the value 1 in for x to work out a specific number. PS, that's the gradient of the function at x equals 1. It's the gradient of f. And then question 4, similar, but it's -2 you'll be substituting in. So again, find the derivative. Number 2, substitute the value. And just FYI, you don't need to write this down, but that would be the gradient of f of x at that point. Any questions? Okay, every second one? If you get to the end of question 4 before it's recess time, then go back and backfill with ones that you think look difficult, but don't move on to question 5. So questions 1 to 4, every second one. And you know what? Let's have, it's really exciting. You could do A and then C and then E, or you could do B, then D, then F. I know, right? So you go crazy and choose your own pathway from here. And I'll come around and help people individually. Okay, get into it.